Tonight, we're going to talk about the most dangerous object in the known universe. It's not a black hole, it's not a supernova, it's something far stranger. Imagine a star so extreme that its magnetic field could erase every credit card on Earth from half the distance to the moon. A star so violent that a single outburst can release more energy in 1/10 of a second than our sun produces in 250,000 years. A star so dense that a single teaspoon of its material weighs more than Mount Everest. These objects are real. They exist in our galaxy right now. And if one were close enough, it wouldn't just threaten life on Earth. It would rearrange the very atoms inside your body. They're called Magnetars, and their story is terrifying. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To understand why magnetars are so dangerous, you first need to understand what they are. And to understand what they are, you need to understand how they're born. Because a magnetar doesn't just appear out of nowhere. It's forged in one of the most violent events the universe is capable of producing. The death of a massive star. And the story of that death begins millions of years earlier, with the star's birth. Stars form from enormous clouds of gas and dust floating in the dark spaces between existing stars. These clouds are called nebulae, and they're made mostly of hydrogen and helium left over from the Big Bang, mixed with heavier elements that were scattered into space by previous generations of stars that lived and died before our sun even existed. These clouds can stretch across dozens or even hundreds of light years. They're cold, dark, and incredibly diffuse. If you were floating inside one of these clouds, you wouldn't even notice it. The gas is spread so thin that it's actually a better vacuum than anything we can create in any laboratory on Earth. There are fewer particles per cubic inch in most of these clouds than in the most perfect vacuum chamber humans have ever built. But gravity is patient. Relentlessly, endlessly patient. Over millions of years, gravity slowly pulls the gas together. Small clumps attract more gas. Those clumps grow larger, pulling in even more material from their surroundings. As the gas collapses inward, it heats up. Compression always generates heat. That's why a bicycle pump gets warm when you pump air into a tire. The same principle applies here, just on a scale that's almost impossible to imagine. The center of the collapsing cloud gets hotter and hotter, denser and denser. Eventually, when the temperature at the core reaches about 10 million degrees, something extraordinary happens. Hydrogen atoms begin to fuse together. Nuclear fusion is the process that powers every star in the universe. When hydrogen nuclei, which are just individual protons, slam into each other at extreme speeds, they can overcome their natural electrical repulsion and merge together, forming helium. This process releases an enormous amount of energy, according to Einstein's famous equation, E equals mc squared. A tiny amount of mass is converted into a tremendous amount of energy with every fusion reaction. Individually, each reaction converts only a minuscule fraction of the hydrogen's mass into energy. But when you have trillions upon trillions of these reactions happening every second in the stellar core, the total energy output is staggering. This energy radiates outward as light and heat, and it also creates an outward pressure that pushes against the inward pull of gravity. This is what a star fundamentally is. It's a constant battle between two forces, gravity pulling everything inward, trying to crush the star down into a tiny point, and the energy from nuclear fusion pushing everything outward, trying to blow the star apart. As long as these two forces are balanced, the star remains stable. It shines steadily, converting hydrogen into helium in its core, radiating light and energy into space. This balance is called hydrostatic equilibrium, and it can last for millions or even billions of years, depending on how massive the star is. Our Sun has been maintaining this balance for about 4.5 billion years. It's a relatively modest star, about 864,000 miles across, containing about 330,000 times the mass of Earth. The Sun fuses roughly 600 million tons of hydrogen into helium every single second. That sounds like an enormous rate of consumption, and it is, but the Sun is so incredibly massive that it has enough hydrogen fuel to keep doing this for another 5 billion years or so, before it starts to run low. But the Sun is not the kind of star that creates a magnetar. The Sun is too small, too gentle, too ordinary. When the Sun eventually runs out of hydrogen fuel in its core, it will swell into a red giant, expanding enormously until it engulfs the orbits of Mercury and Venus, and possibly reaches Earth. It will shed its outer layers into space, creating a beautiful glowing shell called a planetary nebula. And at its center, it will leave behind a small, dense remnant called a white dwarf. A white dwarf is about the size of Earth, but contains roughly half the mass of the Sun. It's dense, certainly, but it's not nearly dense enough to become a neutron star, let alone a magnetar. The Sun will die quietly, fading slowly over trillions of years, cooling from white-hot to yellow to red, and eventually to black. A cold, dark cinder drifting silently through space forever. To create a magnetar, you need a much larger star. A star at least 8 times more massive than the Sun, and probably much more than that. Some astrophysical models suggest that the stars most likely to produce magnetars might be 25 to 40 times the mass of the Sun, or even higher. These are the true giants of the stellar world. They're enormous, blindingly luminous, and incredibly hot. A star 20 times the mass of the Sun might have a surface temperature exceeding 50,000 degrees Fahrenheit, compared to the Sun's roughly 10,000 degrees. It would shine tens of thousands, or even hundreds of thousands of times brighter than the Sun. You could see such a star with the naked eye from hundreds of light years away. If you somehow replace the Sun with one of these massive stars, the inner planets, Mercury, Venus, Earth, and possibly Mars, would be bathed in so much ultraviolet radiation and stellar wind that their surfaces would be sterilized and stripped almost instantly. But here's the crucial thing about massive stars that determines their fate. They burn through their fuel much faster than smaller stars. You might think a bigger star with more fuel would last longer. It seems like a reasonable assumption. A bigger gas tank should mean a longer drive. But the opposite is true for stars. A massive star's core is so hot and so dense that fusion reactions happen at an enormously accelerated rate. The rate of energy production doesn't increase in proportion to mass. It increases roughly as mass raised to the 3rd or even the 4th power. A star that's 20 times more massive than the Sun doesn't burn its fuel 20 times faster. It burns it roughly thousands of times faster. The Sun will burn for about 10 billion years total. A star 20 times the Sun's mass might burn through all its fuel in only about 10 million years. That might still sound like a long time from a human perspective, but in cosmic terms, it's almost nothing. The Sun has already lived 450 times longer than such a star's entire lifespan. Massive stars live fast, burn with furious brightness, and die in spectacular violence. And the way they die is what matters for our story tonight. Because as a massive star ages, something remarkable happens deep inside its core. A process that sets the stage for one of the most extreme objects in the known universe. When a massive star exhausts the hydrogen in its core, it doesn't simply stop and die. Instead, the core contracts under its own gravity, heating up even further. When the temperature reaches about 100 million degrees, the helium nuclei that were produced from millions of years of hydrogen fusion begin to fuse together, creating carbon and oxygen. This helium fusion produces energy that stabilizes the core temporarily, halting the gravitational collapse. The star adjusts to its new reality, finding a fresh equilibrium at a higher temperature and greater density. But helium fusion produces less energy per reaction than hydrogen fusion did. And because the core is now hotter and denser, the star burns through its helium supply faster than it burned through its hydrogen. When the helium runs out, the core contracts again, heating up to even more extreme temperatures. At about 500 million degrees, the carbon nuclei begin to fuse, producing neon and magnesium. When the carbon is consumed, the core contracts yet again, and neon fusion begins at about 1.5 billion degrees. Then oxygen fusion kicks in at roughly 2 billion degrees. Then silicon fusion at about 3 billion degrees. Each successive fuel burns faster than the one before it, and produces less energy per reaction. What's happening inside the star at this point is one of the most extraordinary structures in all of nature. The core has developed a layered architecture, like the layers of an onion. At the very center, silicon is fusing into iron and nickel. Surrounding that is a shell where oxygen is still fusing. Outside that, a shell of neon fusion, then carbon, then helium, then hydrogen at the outermost layer, still burning steadily, completely oblivious to the drama unfolding deep below. Each shell is burning a different nuclear fuel at a different temperature, a different density, and a different rate. The temperatures increase dramatically as you move inward, reaching several billion degrees at the very center, while the outer hydrogen-burning shell sits at a comparatively cool 10 million degrees. The star at this point is living on borrowed time, and the clock is accelerating with terrifying speed. Each successive fuel lasts a dramatically shorter period than the one before. Hydrogen burning in the core lasted millions of years. Helium burning lasted perhaps a few 100,000 years. Carbon burning might last a few hundred years. Neon burning lasts roughly a single year. Oxygen burning lasts maybe 6 months. And silicon burning, the very final stage of nuclear fusion, lasts only about 1 day. 1 day. After millions of years of steady burning, the star's core runs through its last usable fuel in roughly 24 hours. And then something catastrophic happens. Something that changes everything in less than a heartbeat. Silicon fusion produces iron, and iron is the absolute end of the line. This is one of the most important facts in all of astrophysics. Every element lighter than iron on the periodic table releases energy when you fuse it into something heavier. That's what has been powering the star through every stage of its life. But iron is fundamentally different. Iron has the most tightly bound nucleus of any element in the universe. Its protons and neutrons are held together more strongly than in any other atom. Fusing iron into anything heavier doesn't release energy. It requires energy. It absorbs energy instead of producing it. You could think of iron as nuclear ash. It's the final end product of stellar fusion, the residue left behind when everything that can burn has burned. It's useless fuel, dead weight. This means the star suddenly has no way to generate the outward pressure that has been holding it up against its own gravity for millions of years. The core has been building up iron like ash accumulating at the bottom of a furnace. Iron that cannot burn. Iron that just sits there, growing heavier and heavier by the hour. When the iron core reaches a critical mass of about 1.4 times the mass of the Sun, a threshold known as the Chandrasekhar limit, all compressed into a region roughly the size of Earth, the end comes with terrifying, almost incomprehensible speed. In less than a single second, the core collapses. Not slowly, not gradually. It collapses at speeds approaching a quarter of the speed of light, roughly 45,000 miles per second. The iron nuclei are crushed so violently that the electrons and protons in the atoms are forced together, merging to form neutrons in a process called neutronization or inverse beta decay. This process releases a flood of ghostly particles called neutrinos. In that fraction of a second, the entire core of the star transforms from a ball of iron roughly the size of Earth into a ball of almost pure neutrons, roughly the size of a city. A sphere about 12 miles across. 12 miles. That's smaller than many metropolitan areas on Earth. Manhattan Island is about 13 miles long. The entire mass of the collapsed core, more mass than our entire Sun, compressed into an object you could almost drive across in 15 minutes on a highway. The density of this object defies every normal frame of reference. A single teaspoon of neutron star material would weigh roughly 6 billion tons. 6 billion tons in a teaspoon. If you could somehow transport a teaspoon of this material to Earth's surface, it would weigh significantly more than Mount Everest. It would immediately punch through whatever surface it landed on, boring through concrete, through bedrock, through the Earth's crust and mantle, sinking all the way to the center of the planet because nothing on Earth could support that kind of concentrated weight. The collapse happens so fast that the outer layers of the star don't even register that it's occurred. Information can only travel through the star at the local speed of sound in that material, and the core has already finished collapsing before the outer layers can respond. There's a bizarre fraction of a second where the outer layers of the star are still hanging in space, still fusing elements in their shells, completely unaware that the floor has just vanished from beneath them. Then gravity takes hold. They begin to fall. The infilling material plummets toward the center of the star at a significant fraction of the speed of light. Hundreds of millions of tons per second raining inward. And then it slams into the newly formed neutron star. The neutrons packed into that tiny sphere resist any further compression through a quantum mechanical effect called neutron degeneracy pressure. The neutron star has become an almost perfectly rigid wall, harder and more unyielding than anything else in nature. And the infalling outer layers of the star hit that wall at tens of thousands of kilometers per second. They bounce violently. This rebound creates a shock wave that begins tearing through the star from the inside out. The shock wave initially stalls, however, as it fights against the enormous weight of material still falling inward. But it's reinforced and ultimately revived by the colossal flood of neutrinos streaming outward from the collapsing core. Neutrinos are ghostly particles that barely interact with normal matter under ordinary circumstances. A neutrino could pass through a wall of solid lead a light year thick, without touching a single atom. But the conditions inside a collapsing star are so extreme, so unimaginably dense, that even neutrinos deposit a small fraction of their energy into the surrounding material. And the sheer number of neutrinos produced in the collapse is beyond comprehension. Roughly 10 to the 58 neutrinos are released in about 10 seconds. Even though each one deposits only a tiny sliver of its energy, the cumulative effect is enough to revive the stalled shockwave and drive it outward with devastating force. The result is a supernova. The outer layers of the star are blown outward at speeds of 10,000 to 30,000 kilometers per second. The explosion is so powerful that for a few weeks, this single dying star can outshine an entire galaxy containing hundreds of billions of stars. The energy released in the visible explosion alone is staggering, roughly equivalent to the total energy our sun will produce over its entire 10 billion year lifetime, all released in seconds. And the full energy of the event, including the invisible flood of neutrinos, is about 100 times greater still. The explosion scatters the star's outer layers across light years of interstellar space. All those elements forged in the star's core over millions of years. The carbon, the oxygen, the silicon, the iron, plus even heavier. Elements synthesized in the supernova explosion itself, like gold, platinum, uranium, and dozens of others, are flung outward into the void. This enriched material will eventually seed new clouds of gas and dust, which will collapse to form new stars and new planets. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was created inside a massive star and scattered into space by a supernova billions of years ago. You are, quite literally, built from the remains of dead stars. But tonight we're not interested in what the explosion throws outward. We're interested in what stays behind. At the center of this cosmic catastrophe sits the remnant, the neutron star. A ball of neutrons 12 miles across, containing 1 to 2 times the mass of our sun, spinning rapidly and radiating intense energy across the electromagnetic spectrum. The rapid spin is a consequence of the conservation of angular momentum, one of the most fundamental principles in physics. It's the same principle that makes an ice skater spin faster when she pulls her arms in close to her body. The original massive star was rotating, perhaps completing one full revolution every few weeks or months, when its core collapsed from something the size of Earth to something the size of a small city, a reduction in radius by a factor of roughly 1,000. That rotation sped up by an enormous factor. A neutron star can be born spinning hundreds of times per second. The fastest known spinning neutron star rotates about 716 times per second. Think about that carefully. An object containing more mass than the sun, compressed into a sphere 12 miles across, completing more than 700 full rotations every single second. The surface at the equator of such a rapidly spinning neutron star would be moving at a substantial fraction of the speed of light. And this is where things cross the threshold from extreme to truly unprecedented. Because not all neutron stars are the same. Most neutron stars become what astronomers call pulsars. Pulsars have powerful magnetic fields, typically around 1 trillion gauss, roughly 1 trillion times stronger than Earth's magnetic field of about half a gauss. That is already staggeringly intense. A pulsar's magnetic field would be deadly to any biological organism at distances of thousands of miles. But compared to what we're about to discuss, a pulsar's magnetic field is practically gentle. Under certain specific conditions that scientists are still working to fully understand, Something extraordinary happens in the first 10 to 30 seconds after a neutron star is born. The interior of the newly formed neutron star is unimaginably hot, reaching temperatures of hundreds of billions of degrees. At these temperatures, the neutron-rich fluid inside the star is violently turbulent, churning and convecting with ferocious energy like water in a pot that's been brought to an absolutely furious boil. And crucially, different layers of the neutron star may be rotating at slightly different speeds, a condition physicists call differential rotation, where the inner core spins at one rate while the outer layers spin at another. This combination of extreme heat, violent convection, and differential rotation creates what physicists call a convective dynamo. A dynamo is a self-amplifying feedback process where the motion of electrically conducting fluid generates and strengthens magnetic fields, and those strengthened magnetic fields in turn influence the fluid's motion, which generates even stronger fields. The process feeds on itself, growing exponentially in intensity. The same basic principle operates inside Earth, where the slow churning of liquid iron in our planet's outer core generates Earth's magnetic field of about half a gauss at the surface. But the dynamo operating inside a newborn neutron star works under conditions so far beyond what exists inside Earth that the comparison becomes almost meaningless. In those first critical seconds after the neutron star's birth, this convective dynamo amplifies the magnetic field by factors of thousands or even millions. It converts the rotational energy and thermal energy of the neutron star into magnetic energy, building the field to strengths that would be impossible to produce through any other known mechanism in the universe. The magnetic field of the resulting object can reach up to 1 quadrillion gauss. That is 1 followed by 15 zeros. A quadrillion is a million billion. It's a number so large that it barely registers as meaningful. To give you a sense of just how far beyond human experience this is, the most powerful magnetic fields we have ever managed to create in any laboratory on Earth, using the most advanced technology our civilization possesses, are billions of times weaker than a Magnetars field. The gap between what we can produce and what a magnetar produces is not a gap that better engineering could close. It's a chasm that reflects the difference between human-scale physics and the physics of collapsed stars. This extraordinary amplification doesn't happen in every neutron star. It requires a very specific and perhaps rare set of conditions. The initial rotation rate must be fast enough to drive vigorous differential rotation between layers. The temperature must be high enough for powerful convective churning. The internal composition and structure must support the right kind of fluid dynamics. If any of these conditions aren't met, the neutron star becomes an ordinary pulsar. Certainly powerful and dangerous by any earthly standard, but not a magnetar. Scientists estimate that only a small fraction of neutron stars are born with the right conditions to become a magnetar. The precise fraction is still debated, but magnetars are clearly rare. Out of the enormous population of neutron stars in the Milky Way, only a handful of magnetars have been confirmed through observations, though many more almost certainly exist in quiet phases that make them extraordinarily difficult to detect. When the dynamo process is successful, the result is a magnetar. A neutron star with a magnetic field so overwhelmingly powerful that it doesn't just influence its surroundings, it dominates them completely, it warps them, it fundamentally changes the nature of matter, energy, and even empty space in its vicinity. The word magnetar combines magnetic and star, And it's a fitting name for what might be the most extreme object nature has ever produced. When the theory behind these objects was first proposed, many astronomers were deeply skeptical. Fields that strong seemed physically implausible, perhaps even impossible. But observation after observation confirmed that these objects were real, and that their magnetic fields were every bit as extreme as the theory suggested. A magnetar is tiny, just 12 miles across. You could fit it comfortably inside the boundaries of a single city, and yet this minuscule object contains more mass than the entire sun. It spins rapidly, though generally slower than the fastest pulsars, because its intense magnetic field radiates energy so powerfully that it acts as a brake on the star's rotation, gradually slowing it down over thousands of years. And it possesses a magnetic field so overwhelmingly strong that it can do things to matter, to atoms, to light, and to the very fabric of empty space itself that nothing else in the known universe can do. This is the most dangerous type of star that exists. Not because of its size, which is tiny, not because of its temperature, though it is extremely hot, not even because of its almost incomprehensible density. It's dangerous because of that magnetic field. A field so powerful that it doesn't merely attract metal objects like some cosmic refrigerator magnet. It reshapes the fundamental structure of atoms. It distorts the behavior of light passing nearby. It stores colossal amounts of energy within the star's rigid crystalline crust, and then releases that energy in catastrophic eruptions that can be detected across the entire galaxy and beyond. The birth of a magnetar requires the death of a giant star, a supernova explosion of almost inconceivable power, and a perfect storm of physical conditions in the first heartbeats of a neutron star's existence. The result is an object that packs the mass of the sun into a space the size of a small city, spins hundreds of times per second, and generates a magnetic field billions of times stronger than anything humans have ever produced or could ever hope to produce. And that magnetic field is what makes magnetars not just scientifically interesting, not just cosmically impressive, but genuinely profoundly dangerous to anything that exists in their vicinity. Because the things that field can do to matter, to energy, and to the quantum vacuum of space itself go far beyond anything our everyday experience on this small, safe, magnetically gentle planet could ever prepare us to imagine. So now we know what a magnetar is. A neutron star born from the violent death of a massive star, forged in the fires of a supernova, and blessed, or perhaps cursed, with a magnetic field amplified to almost unimaginable intensity in the first seconds of its existence. But knowing that a magnetar has an incredibly strong magnetic field doesn't really tell you much unless you understand what that actually means. What does a magnetic field that powerful actually do? How does it compare to the magnetic fields we encounter in everyday life? And what happens to matter, to light, to the very fabric of empty space when it's subjected to forces this extreme? To answer these questions, we need to build a ladder of magnetic strength. We need to start with what we know, with the magnetic fields we experience every day, and climb rung by rung towards something so far beyond our experience that even physicists struggle to fully wrap their heads around it. Let's start at the bottom of the ladder. Earth has a magnetic field. You've probably used it without thinking about it every time you've looked at a compass. A compass needle aligns itself with Earth's magnetic field, pointing roughly north. This field is what protects us from the solar wind, the stream of charged particles constantly flowing outward from the sun. Without Earth's magnetic field, the solar wind would gradually strip away our atmosphere, just as it stripped away the atmosphere of Mars after Mars lost its own magnetic field billions of years ago. Earth's magnetic field is essential for life. It's our invisible shield against the harshness of space. But Earth's magnetic field is incredibly weak. At the surface, it measures about half a gauss. The gauss is a unit of magnetic field strength, named after the German mathematician Carl Friedrich Gauss. Half a gauss is enough to move a compass needle, enough to deflect charged particles from the sun, but it's barely anything in terms of raw magnetic force. You don't feel it. It doesn't affect the objects around you in any noticeable way. It doesn't pull metal toward the ground or make your keys stick to the floor. Half a gauss is gentle, almost imperceptibly gentle. Now let's go up a step. A typical refrigerator magnet has a magnetic field of about 50 gauss. That's about 100 times stronger than Earth's magnetic field. 50 gauss is enough to hold a piece of paper against a metal surface. It's enough to stick a photo to your fridge door, but it's not enough to do much else. You can hold a refrigerator magnet in your hand without feeling anything unusual. It doesn't affect your body in any way. It doesn't change the behavior of the atoms in your skin or the molecules in your blood. 50 gauss is a casual, everyday magnetic field. Nothing to worry about. Moving up the ladder, a strong bar magnet or a horseshoe magnet, the kind you might have played with in school, produces a field of a few hundred to maybe 1,000 gauss. At this strength, the magnet can attract iron objects from a short distance, pull paper clips across a table, and stick firmly to a steel surface. 1,000 gauss sounds impressive compared to Earth's half gauss field, but it's still completely harmless to human beings. You can hold a magnet this strong against your body all day and experience absolutely no ill effects. The magnetic field passes right through your flesh without doing anything because the atoms in your body aren't magnetic enough to respond to a field this weak. Now let's take a bigger jump. Medical MRI machines, the ones used to image the inside of your body without surgery, use magnetic fields of about 15,000 to 30,000 gauss. That's 1.5 to 3 Tesla, where 1 Tesla equals 10,000 gauss. These are powerful magnets, powerful enough that if you bring a metal object into the MRI room, it can be ripped from your hands and pulled violently toward the machine. There have been cases where oxygen tanks, wheelchairs, and even hospital beds have been pulled across the room and slammed into MRI machines with enough force to cause serious damage and even fatal injuries. The magnetic field of an MRI machine demands respect, and yet, even at 30,000 gauss, the magnetic field doesn't affect your body's atoms in any harmful way. Your body is mostly made of water, and water molecules aren't strongly magnetic. The MRI works by aligning the nuclear spins of hydrogen atoms in your body and then detecting the signals they emit when they relax back to their normal state. But the field doesn't damage the atoms themselves. It doesn't change their structure. It doesn't alter your chemistry. People have been scanned in MRI machines millions of times with no harmful effects from the magnetic field itself. 30,000 gauss is strong by everyday standards, but it's still far too weak to affect the fundamental structure of atoms. The strongest sustained magnetic fields ever produced in a laboratory on Earth reach about 450,000 gauss, or 45 Tesla. These fields are produced by enormous electromagnets at facilities like the National High Magnetic Field Laboratory in Tallahassee, Florida. These magnets require massive amounts of electrical power and sophisticated cooling systems to operate. But even well below this record, remarkable effects appear. At about 16 Tesla, scientists have levitated living creatures, including frogs. The famous levitating frog experiment, conducted by André Geim at Radboud University in the Netherlands in 1997, demonstrated that a sufficiently strong magnetic field can make water and living tissue float by exploiting their weak diamagnetic properties. The frog was completely unharmed, but the demonstration showed that even at field strengths far below the laboratory maximum, magnetism starts to interact with matter in ways that are noticeable and surprising. The strongest pulsed magnetic fields produced in controlled indoor experiments, where the equipment is blown apart by its own magnetic forces after only a fraction of a second, have reached about 1200 Tesla, or 12 million Gauss. Outdoor experiments using high explosives to compress magnetic fields have briefly reached even higher values, but the results are far harder to measure precisely. These fleeting bursts last for microseconds before the apparatus tears itself to pieces. At these field strengths, the magnetic pressure, the actual physical force exerted by the field on surrounding matter, becomes enormous. The magnets literally explode. The metal coils that generate the field are ripped apart by their own magnetic forces, faster than the speed of sound in the metal. This is the absolute upper limit of what human technology can produce. 12 million Gauss for a fraction of a second before everything is destroyed. Remember that number? Hold it in your mind. Now let's talk about a magnetar. A magnetar's magnetic field reaches up to 1 quadrillion Gauss. That is 10 to the 15th power Gauss. 1 followed by 15 zeros. To compare that to the strongest field humans have ever produced, even in those fleeting destructive experiments, a magnetar's field is about 100 million times stronger. 100 million times stronger than a magnetic field so powerful it destroys the equipment that creates it in microseconds. The strongest sustained field in a laboratory is 45 Tesla. A magnetar's field can reach 100 billion Tesla. The difference between these numbers is so vast that comparisons become almost meaningless. Let me try to put this in perspective another way. If you took the strongest MRI magnet in the world, the most powerful medical imaging device ever built, and you wanted to match the magnetic field of a Magnetars, you would need to make that magnet roughly 300 million times more powerful. If each MRI machine weighs several tons and fills an entire room, imagine 300 million of those machines all concentrated into a space 12 miles across. And even that mental image doesn't capture the reality because magnetic fields don't simply add up when you put magnets next to each other. The physics of generating a field this strong is fundamentally different from anything we can do on Earth. Here is one more comparison to try to make this real. The magnetic field of a typical pulsar, an ordinary neutron star, is about 1 trillion Gauss. That's already an absurdly powerful field, 1 trillion times stronger than Earth's. A magnetar's field is roughly 1,000 times stronger than even that. So a magnetar doesn't just exceed human technology by an incomprehensible margin. It exceeds the already extraordinary magnetic fields of ordinary neutron stars by a factor of 1,000. It sits at the absolute apex of magnetic intensity in the known universe. Nothing we have ever detected, nothing we have any theoretical reason to expect, produces a stronger sustained magnetic field than a magnetar. Now that you have some sense of the scale we're dealing with, let's talk about what a magnetic field this powerful actually does. because the effects are not just extreme versions of what ordinary magnets do. At magnetar field strengths, entirely new physical phenomena emerge. Things happen that don't happen anywhere else in the known universe. The rules change. Let's start with what the field does to the magnetar itself. The magnetic field of a magnetar isn't just floating around the star like some sort of invisible aura. It's anchored deep within the star's structure, threaded through the incredibly dense material of the neutron star's crust and core. The crust of a neutron star is made of a crystalline lattice of atomic nuclei and free electrons, compressed to densities far beyond anything that exists on Earth. This crust is about a mile thick, and it's incredibly rigid. It is, in fact, the strongest solid material in the known universe. No force available on Earth could break it, bend it, or deform it. It is a material of almost incomprehensible structural perfection, and yet, the magnetic field of a magnetar is strong enough to stress this unbreakable crust to its limits. The magnetic field lines thread through the crust, and as the field evolves over time, as field lines shift and reconfigure, they exert enormous forces on the crustal material. The energy stored in a magnetar's magnetic field is staggering. The total magnetic energy in a magnetar can be comparable to the total energy output of the sun over several 100,000 years, all stored in the magnetic field of an object 12 miles across. That is an almost inconceivable amount of energy locked inside a space smaller than a city. This energy doesn't just sit there passively, it pushes and pulls on the crust, building up stress over time. The magnetic field wants to rearrange itself into a simpler configuration, but the crust resists. The field pushes harder. The crust holds firm, and the tension between these two forces, the irresistible magnetic pressure and the immovable crystalline lattice, builds and builds until something has to give. What happens when it gives is among the most violent events in the universe. The magnetic field also extends far beyond the surface of the star, reaching out into the surrounding space. The region of space dominated by a magnetic field is called the magnetosphere. For a magnetar, this magnetosphere is enormous relative to the star's tiny physical size. The magnetic field fills a volume thousands of times larger than the star itself, creating a zone of extreme magnetic influence that anything passing through would be profoundly affected by. And the first thing that magnetic field affects is something you might not expect. It affects empty space itself. According to quantum mechanics, empty space isn't truly empty. Even in a perfect vacuum, with every atom and particle removed, space is filled with what physicists call quantum fluctuations. Virtual particles are constantly popping into existence in pairs, a particle and its antiparticle appearing together for the briefest instant, before annihilating each other and vanishing again. This happens everywhere, all the time, throughout the entire universe. It's a fundamental property of quantum mechanics confirmed by experiments. Under normal conditions, these quantum fluctuations are symmetric in all directions. They don't favor any particular orientation. Empty space looks the same no matter which direction you examine it. But a sufficiently strong magnetic field can change this. The field can interact with these virtual particles, forcing them to align with the field direction. This breaks the symmetry of empty space. The vacuum itself becomes birefringent. Birefringence is a property where light traveling through a material experiences different refractive indices depending on its polarization. Some crystals on Earth, like calcite, are birefringent, If you place a piece of calcite on top of a printed word, you see the word doubled because light polarized in one direction bends differently than light polarized in another direction. The crystal splits the light into two separate beams. A magnetar's magnetic field does the same thing to empty space, not to a crystal, not to any material, to the vacuum itself. Light passing through the magnetosphere of a magnetar gets split into two polarization components that travel at very slightly different speeds. This phenomenon is called vacuum birefringence, and it was predicted by quantum electrodynamics, the theory that describes how light and matter interact at the quantum level. For decades, vacuum birefringence was a theoretical prediction that had never been observed because it requires magnetic fields far stronger than anything available in any laboratory on Earth. In 2017, astronomers using the European Southern Observatory's Very Large Telescope reported the first observational evidence of vacuum birefringence around a neutron star. They observed a neutron star called ARXJ 1856.5 - 3754 and detected polarization effects in its light, consistent with the predictions of vacuum birefringence. This was a landmark observation. For the first time, scientists had evidence that magnetic fields could alter the properties of empty space itself, exactly as quantum electrodynamics had predicted. Around a magnetar, this effect is far more pronounced than around an ordinary neutron star. The magnetic field is so strong that the vacuum becomes significantly birefringent. Light doesn't just split subtly, it's noticeably affected. Photons traveling through a magnetar's magnetosphere experience the vacuum as if it were a strange anisotropic medium, not empty space at all. The vacuum near a magnetar has optical properties. It bends light. It affects how electromagnetic radiation propagates. Empty space near a magnetar isn't really empty in any meaningful sense. The magnetic field has given the vacuum structure, has imposed its own properties onto nothingness itself. This is one of the most profound things a magnetar does. It reveals that empty space has hidden properties, properties that only emerge under the most extreme conditions. Under normal circumstances, in the weak magnetic fields that exist on Earth, or even in the fields of ordinary magnets, these properties are completely invisible. They have no measurable effect. But crank the field up to magnetar levels, and suddenly the vacuum has texture. It has direction. It has optical properties. The magnetic field has, in a very real sense, changed the nature of space itself. But the effects on empty space, as remarkable as they are gentle compared to what a magnetar's field does to actual matter. Because when atoms encounter a magnetic field this strong, they stop being atoms as we know them. You probably learned in school that atoms consist of a central nucleus containing protons and neutrons, surrounded by a cloud of electrons. In the standard picture, electrons occupy orbitals, which are probability clouds describing where the electron is likely to be found at any given moment. These orbitals have characteristic shapes. The lowest energy orbital, called the s orbital, is spherical. Higher energy orbitals are shaped like dumbbells or more complex patterns. The shapes of these orbitals determine how atoms bond with each other, which determines all of chemistry. Every molecule, every material, every chemical reaction in your body depends on the shapes and arrangements of electron orbitals. In a normal magnetic field, even a strong one by human standards, electron orbitals are barely affected. The electrons might shift slightly in response to the field, but the overall structure of the atom remains intact. Chemistry continues to work normally. Molecules form the same way they always do. This is why you can sit inside an MRI machine with a magnetic field of 30,000 Gauss, and your body's chemistry is completely unaffected. The field isn't strong enough to significantly alter electron orbitals. But at magnetar field strengths, everything changes when the magnetic field reaches about 10 billion Gauss, which is still well below the maximum magnetar field strength. The magnetic force on electrons becomes comparable to or even exceeds the electrical force that binds them to the atomic nucleus. This is the critical threshold. This is where atoms stop being atoms as we understand them. In a field this strong, the electrons are no longer free to occupy their normal spherical or dumbbell-shaped orbitals. The magnetic field forces them into tight circular orbits around the magnetic field lines. Instead of forming a roughly spherical cloud around the nucleus, the electrons are squeezed into extremely narrow, cylindrical distributions aligned with the field. The atom, which under normal conditions is roughly spherical, becomes elongated, stretched out like a needle along the direction of the magnetic field. At around 10 trillion Gauss, a strength within the range of the most powerful magnetar fields, hydrogen atoms become roughly 200 times longer than they are wide. They're no longer recognizable as atoms in any normal sense. They're thin needles of charge, stretched along the field lines, their electron distributions compressed into regions so narrow that the behavior of the electron is essentially one-dimensional. The electron can only move along the field line. Its motion perpendicular to the field is frozen by the overwhelming magnetic force. This has devastating consequences for chemistry. The shapes of molecules depend entirely on the shapes of the atomic orbitals that form the chemical bonds. When those orbitals are distorted into narrow cylinders, the rules of chemistry change completely. The familiar molecular structures that make up everything we know, water molecules, organic compounds, the double helix of DNA, all of these depend on atoms being roughly spherical and forming bonds at specific angles. In a magnetar's field, none of these structures could exist. Water molecules couldn't form in their normal V-shape. Carbon atoms couldn't form the tetrahedral bonds that underpin organic chemistry. The complex molecular machinery of life would be impossible. Instead of normal chemistry, magnetar strength fields create entirely new types of molecular bonds that don't exist anywhere else in the universe. Atoms can form unusual elongated molecules aligned along the field direction. Hydrogen atoms can form chain-like polymers, long threads of hydrogen nuclei sharing electrons in cylindrical orbitals along the field line. Other elements present on or near a neutron star's surface, like iron and carbon, also form exotic configurations. Iron atoms, which under normal conditions have 26 electrons arranged in complex orbital shells, are squeezed into pencil-thin structures where all 26 electrons stack into narrow, cylindrical orbits. The resulting iron atom would be unrecognizable to any chemist on Earth. These exotic atomic and molecular structures have been studied theoretically by physicists, but they bear no resemblance whatsoever to chemistry as it operates on Earth or anywhere else with normal magnetic fields. This means that at the surface of a magnetar, or anywhere within this magnetosphere where the field is strong enough, matter as we know it cannot exist. Not just life, not just complex molecules, even simple familiar atoms are fundamentally altered. The periodic table still applies in the sense that the same elements exist, the same numbers of protons. electrons. But the way those electrons arrange themselves around the nucleus is completely different. It's as if the rules of chemistry have been rewritten from scratch. Here is another way to think about just how extreme this is. The strength of a magnetic field can be compared to the strength of the electric field inside an atom by using something called the critical quantum magnetic field, sometimes referred to as the Schwinger limit for electron interactions. This is the magnetic field strength at which the magnetic energy associated with an electron equals the electron's rest mass energy. It's about 4.4 times 10 to the 13th Gauss, or about 44 trillion Gauss. Below this value, magnetic effects are a perturbation, a small nudge to the atom's normal structure. Above this value, the magnetic field becomes the dominant force controlling the electron's behavior, and the electrical attraction of the nucleus becomes secondary. Many magnetars have fields that approach or even exceed this critical threshold. When a magnetar's field reaches or surpasses 44 trillion Gauss, the magnetic field is no longer just affecting atoms, it's dominating them. The electron's relationship to the nucleus, which normally determines everything about how atoms work, becomes secondary to the electron's relationship with the magnetic field. The atom becomes a creature of the magnetic field rather than a creature of the nucleus. This is a fundamental transformation. It's not just that atoms are distorted. The hierarchy of forces that governs their structure has been inverted. The effects on light are equally dramatic. In a magnetar's field, photons can do things that seem almost magical by the standards of everyday physics. One of the most striking effects is called photon splitting. In empty space, under normal conditions, a photon cannot spontaneously split into two photons. This process is forbidden by the symmetry of the vacuum. A single photon cannot become two photons while conserving energy and momentum under normal circumstances. But in a magnetar's field, the broken symmetry of the vacuum allows this process to occur. A single photon entering the magnetosphere of a magnetar can split into two lower energy photons. This has real consequences for the radiation that escapes from a magnetar's surface. The spectrum of light emitted by the star is modified by photon splitting as the light passes through the intense field near the surface. Another effect is magnetic photon scattering, where the virtual electron-positron pairs in the vacuum can scatter photons in ways that don't happen in field-free space. The magnetic field effectively makes the vacuum slightly opaque. Not completely opaque, but photons interact with the magnetized vacuum in ways that change their direction and polarization. The vacuum near a magnetar is not a passive background. It's an active participant in the physics, scattering and splitting and polarizing light. For high-energy photons, particularly gamma rays, the magnetar's field creates another extraordinary possibility. A gamma-ray photon passing through a sufficiently strong magnetic field can spontaneously convert into an electron-positron pair, a particle of matter and a particle of antimatter appearing from pure electromagnetic energy. This process, called magnetic pair production, requires both a high-energy photon and a very strong magnetic field. Both conditions are abundantly met near a magnetar. The field acts as a catalyst, providing the conditions necessary for the conversion of electromagnetic radiation directly into matter and antimatter. In the vicinity of a magnetar, photons don't just carry energy, they can become matter. Energy transforms into substance, light becomes stuff. This is one of the most vivid demonstrations of Einstein's mass-energy equivalence happening continuously in the wild, not in a particle accelerator, but in the magnetosphere of a dead star. All of these effects, vacuum birefringence, photon splitting, magnetic pair production, and the extreme distortion of atoms are happening simultaneously in the vicinity of a magnetar. The space around one of these objects is a laboratory for extreme physics, a place where phenomena predicted by quantum electrodynamics but never observable under normal conditions become real, measurable, and powerful. A magnetar is a place where the fundamental relationship between matter, energy, and empty space is altered by sheer magnetic force. And we haven't even talked yet about what happens when this incredible magnetic field becomes unstable. Because the field doesn't just sit there passively distorting atoms and bending light. It stores energy, enormous amounts of energy. Energy that builds up in the star's crust, straining against the strongest solid material in the universe. And when that crust finally gives way, when the magnetic field reconfigures and all that stored energy is released at once, the result is one of the most violent events ever observed in the cosmos. The magnetic field of a magnetar is not just a curiosity of extreme physics. It's a loaded weapon, a weapon that can fire across distances measured in light years and affect planets and civilizations that have no idea it even exists. The field distorts atoms, bends light, restructures empty space, and stores vast reservoirs of energy that can be unleashed in catastrophic bursts. This is why magnetars are not just the most extreme type of star. They are, in a very real and measurable sense, the most dangerous. Not because of what they are, but because of what their magnetic field can do to everything around them. And the universe has given us direct evidence of just how destructive these outbursts can be. Evidence that arrived at Earth from across the galaxy, moving at the speed of light, carrying with it a warning about the raw, terrifying power of the most dangerous star in the universe. So now we know what a magnetar's magnetic field does to atoms and to light and to the vacuum of empty space. It distorts atoms into needles, it splits photons, it gives the vacuum optical properties it shouldn't have. These are extraordinary physical effects, unlike anything else in the known universe. But all of these phenomena are, in a sense, passive. They're what the field does simply by existing. They're what happens when matter or light wanders into the magnetar's domain. They're the background hum of a magnetar's presence. What makes magnetars truly dangerous, what elevates them from being merely extreme objects to being the most violent and destructive type of star in the universe, is what happens when the magnetic field becomes unstable. Because a magnetar's field isn't static. It doesn't just sit there in perfect equilibrium forever. It evolves. It shifts. It builds up stress in the star's crust over months or years or decades. And when that stress exceeds what even the strongest material in the universe can withstand, the crust breaks. The field reconfigures. And the energy that's been building up for years is released all at once in an explosion so powerful that it can affect planets on the other side of the galaxy. To understand how this works, you need to understand the relationship between a magnetar's magnetic field and its crust. Remember, a neutron star's crust is made of a crystalline lattice of atomic nuclei, mostly iron and other heavy elements, embedded in a sea of free electrons and neutrons. This crust is about a mile thick, and it's extraordinarily rigid. It's the hardest, strongest solid material known to exist anywhere in the universe. If you could somehow obtain a piece of neutron star crust the size of a sugar cube, it would resist being broken or deformed with a tenacity far exceeding any material on Earth. The crust of a neutron star is estimated to be roughly 10 billion times stronger than the strongest steel we can manufacture. The magnetic field lines of a magnetar are anchored in this crust. They thread through it, passing from the interior of the star outward through the crust and into the magnetosphere beyond. The field isn't smooth and uniform like the field of a bar magnet you'd see in a textbook diagram. It's complex, tangled, with regions of intense concentration and regions where the field lines twist around each other in knots. This tangled structure is a consequence of the violent dynamo process that created the field in the first place. The field was born in chaos, in the turbulent first seconds of the neutron star's life, and it retains that chaotic complexity. Over time, the magnetic field evolves. Field lines want to rearrange themselves into a lower energy configuration, a simpler, more ordered structure. But the crust resists this rearrangement. The field is anchored in the crust, and the crust is rigid. It doesn't want to move. So the field pulls on the crust, trying to drag it into a new configuration, and the crust pushes back, maintaining its shape. This creates stress, enormous, accumulating stress. Think of it like slowly bending a thick sheet of glass. The glass is rigid and strong. It resists bending. As you apply more and more force, the glass flexes slightly, storing elastic energy in its strained structure. From the outside, nothing seems to be happening. The glass looks the same, but internally the stress is building, molecules are being pulled apart, microscopic cracks are forming, and then, suddenly, catastrophically, the glass shatters. All the energy that was slowly building up is released in an instant. The glass doesn't gradually give way. It explodes into fragments. Something similar happens on a magnetar. The magnetic field applies stress to the crust over weeks, months, or years. The crust resists, flexing slightly, storing energy, and then the crust fractures. It cracks. The rigid crystalline lattice breaks along fault lines, suddenly and violently. This is called a starquake. A starquake on a magnetar is not like an earthquake on our planet. Earthquakes on Earth are caused by the motion of tectonic plates, driven by convection currents in the mantle. They release energy stored in the elastic deformation of rock along fault lines. A large earthquake on Earth, a magnitude 9, releases about 10 to the 18th joules of energy. That's an enormous amount of energy by human standards, enough to devastate cities and generate tsunamis that cross entire oceans. But compared to a magnetar starquake, a magnitude 9 earthquake is barely a whisper. A starquake on a magnetar can involve the sudden displacement of the crust by less than a centimeter, less than the width of your finger. On a star that's 12 miles across, a shift of less than a centimeter sounds trivial, almost insignificant, but the forces involved are so extreme, the rigidity of the crust so enormous, that even this tiny displacement releases a staggering amount of energy. A moderate magnetar starquake can release more energy than 1 billion of the most powerful nuclear weapons ever detonated on Earth, all at once. And the larger starquakes, the ones that trigger giant flares, can release as much energy as the sun produces over hundreds of thousands of years, concentrated into a fraction of a second. When the crust cracks, the magnetic field lines that were anchored in the crust suddenly snap into a new configuration. The tangled, stressed field reorganizes itself in a fraction of a second. This rapid reconfiguration of an ultra-strong magnetic field releases all that stored magnetic energy in one violent burst. The energy heats plasma near the star's surface to temperatures of billions of degrees. Electrons and positrons are created in enormous numbers as the intense energy converts into matter and antimatter through the pair production process, where photons in a strong magnetic field spontaneously become particles. A fireball of superheated plasma, electrons, positrons, and intense radiation erupts. There is one more aspect of magnetar violence worth discussing before we move on. ROM, the surface of the star. This is a magnetar flare. Magnetar flares come in different sizes. The smallest are called bursts, brief flashes of X-rays and gamma rays lasting a fraction of a second. These are relatively common for active magnetars. Some magnetars produce dozens or even hundreds of small bursts per year, each one triggered by a minor adjustment of the crust, a small crack, a tiny release of stored magnetic energy. These bursts are detectable by X-ray satellites orbiting Earth, but they're not particularly dangerous at interstellar distances. They're more like the constant creaking and groaning of a structure under immense strain, small releases of pressure that prevent the whole system from failing catastrophically all at once. Then there are intermediate flares. These are larger releases of energy, lasting seconds to minutes, triggered by more significant crustal fractures. Intermediate flares can release as much energy as the sun produces in an entire year, all concentrated into a few seconds of intense X-ray and gamma ray emission. These events are more dramatic, more energetic, and considerably less frequent than the small bursts. An active magnetar might produce an intermediate flare every few months or years. They represent more substantial rearrangements of the magnetic field, larger and deeper cracks in the crust, bigger releases of stored energy. Each intermediate flare is a reminder that the crust is under tremendous strain, that the forces acting on it have not been fully relieved by the smaller bursts, and that the potential for something far worse remains. And then there are the giant flares. These are the events that make magnetars the most dangerous stars in the universe. Giant flares are extraordinarily rare, perhaps occurring only once every few decades or centuries for any given magnetar. But when they happen, they are among the most energetic events ever observed in the cosmos, exceeded only by supernovae and certain types of gamma ray bursts. On December 27th, 2004, the most powerful giant flare ever recorded arrived at Earth. It came from a magnetar designated SGR 1806-20, located approximately 50,000 light-years away on the far side of our galaxy, near the center of the Milky Way. The magnetar was unimaginably distant. 50,000 light-years. The light and radiation from this event had been traveling for 50,000 years before it reached Earth. It left the magnetar when modern humans were still living as hunter-gatherers during the last ice age, long before the invention of agriculture, writing, or civilization. And when it finally arrived at Earth on that December day, it hit our planet with a force that stunned the scientific community. The initial spike of the flare lasted only about 0.2 of a second. In that brief instant, the magnetar released more energy than the sun produces in 250,000 years. Let that sink in for a moment. 250,000 years of solar output, compressed into 1/5 of a second, released by an object 12 miles across, located on the other side of the galaxy. The burst of gamma rays that reached Earth, despite having traveled 50,000 light years and having spread out over an enormous sphere of space during that journey, was still powerful enough to have measurable effects on our planet. The gamma rays ionized the upper layers of Earth's atmosphere, briefly disrupting the ionosphere on the side of Earth facing the burst. The ionosphere is the layer of electrically charged particles in the upper atmosphere that reflects certain radio waves. When the gamma rays from SGR 1806-20 hit, they stripped the electrons from atoms in the ionosphere, temporarily altering its electrical properties. This was detected by instruments monitoring very low-frequency radio signals, which are reflected by the ionosphere. The disruption was brief, lasting only seconds, but it was clearly measurable. Multiple spacecraft detected the event. The burst was so intense that it saturated the detectors on virtually every gamma ray and X-ray satellite in orbit around Earth. These instruments are designed to detect the most energetic events in the universe, and they were overwhelmed. Their detectors maxed out, unable to measure the full intensity of the flare because it exceeded their designed capacity. It was like trying to measure the brightness of an explosion by looking at it through a camera that can't handle the light. The image is just a white blur. The instruments recorded maximum readings across the board, meaning the actual intensity was higher than what they could measure. The flare from SGR 1806-20 was the brightest event from outside our solar system ever recorded by instruments on or near Earth, measured in terms of its apparent intensity, brighter than any observed supernova, brighter than any gamma ray burst previously detected. And it came from a source within our own galaxy, which made its apparent brightness even more remarkable. After the initial spike, the flare continued to emit energy in a pulsating pattern. The radiation from the fireball of hot plasma trapped in the Magnetars' magnetic field pulsated at the star's rotation period of about 7.6 seconds. This meant the Magnetar was spinning, and as it spun, the fireball on its surface rotated in and out of view. The pulsating tail of the flare lasted for several minutes, gradually fading as the trapped plasma cooled and the magnetic field settled into its new configuration. Let's talk about what was happening physically on and around the Magnetar during this event, because the mechanism reveals just how much raw destructive power these objects contain. The giant flare was triggered by a massive fracture of the Magnetar's crust. A large section of the crystalline lattice shattered, allowing the magnetic field to suddenly reconfigure. The magnetic energy that had been building up for years, possibly decades, was released in a fraction of a second. This energy-heated plasma near the star's surface to temperatures exceeding 100 billion degrees. At these temperatures, the thermal energy of individual particles is so extreme that electrons and positrons are produced in abundance through pair creation. The result was an expanding fireball of electrons, positrons, and gamma-ray photons, all trapped within the closed magnetic field lines near the star's surface. This fireball was enormous by the standards of a 12-mile wide star. It extended outward along the magnetic field lines, forming a structure much larger than the star itself. The magnetic field contained the fireball, preventing it from expanding freely into space, but the energy had to go somewhere. Intense radiation, mostly gamma rays and X-rays, poured outward along the open magnetic field lines near the star's poles, creating the initial spike of emission that was detected 50,000 years later on Earth. The trapped fireball gradually cooled, radiating its energy away over the following minutes. As it cooled, it continued to emit X-rays, producing the pulsating tail of the flare. Each pulse corresponded to one rotation of the star, bringing the fireball into and out of the line of sight of distant observers like Earth. Now, let's consider what would have happened if this magnetar were closer. SGR 1806-20 is roughly 50,000 light years away. That's nearly on the opposite side of the galaxy from us. At that distance, the flare was detectable and even briefly affected our ionosphere, but it caused no lasting damage. Earth's atmosphere absorbed the radiation. Life was unaffected. Most people on Earth had no idea anything had happened. But what if the magnetar were closer? Some astronomers have speculated that magnetar flares might be responsible for at least some of the mass extinction events recorded in Earth's geological history. The fossil record shows several major extinction events where large fractions of all species on Earth died out in geologically short periods. The most famous is the extinction that killed the dinosaurs 66 million years ago, which is attributed to an asteroid impact. But other extinction events, like the late Ordovician extinction about 445 million years ago, are less well explained. A gamma-ray event from a relatively nearby magnetar or similar source has been proposed as one possible trigger for some of these mysterious die-offs. The idea remains speculative, but it illustrates the scale of danger these objects represent. If a magnetar producing a giant flare of the magnitude observed in 2004 were located within about 10 light years of Earth, the consequences would be catastrophic. The gamma-ray flux would be billions of times stronger than what Earth received from the 2004 event. The radiation would strip away a significant portion of Earth's ozone layer, the thin shield of ozone molecules in the stratosphere that protects life on the surface from the sun's ultraviolet radiation. Without the ozone layer, intense solar ultraviolet light would reach the surface unfiltered. This radiation would damage the DNA of exposed organisms, cause widespread mutations, trigger cancers in animals, and kill phytoplankton in the upper layers of the ocean. Phytoplankton are the foundation of the marine food web, and also produce a significant fraction of the oxygen in Earth's atmosphere. Their destruction would cascade through the entire biosphere. Computer models suggest that a magnetar giant flare from within about 30 light years could destroy roughly half of Earth's ozone layer. At 10 light years, the destruction would be nearly total. The effects wouldn't be instantaneous. The ozone would be destroyed over a period of hours to days, as the energetic radiation drove chemical reactions in the stratosphere. But the recovery would take years or even decades. During that time, life on Earth's surface would be exposed to dramatically increased ultraviolet radiation from the sun. Land plants would suffer radiation damage. Animals exposed to direct sunlight would develop skin lesions and eye damage. The combination of increased UV radiation and disrupted food chains could trigger a mass extinction event, comparable to the great dying events recorded in Earth's fossil history. At even closer distances, the effects would be more directly lethal. If a magnetar were within 1 light year and produced a giant flare directed toward Earth, the initial burst of gamma radiation could be intense enough to deliver a lethal radiation dose to exposed organisms on the surface facing the burst. The atmosphere would absorb much of the radiation, but enough would penetrate to cause immediate harm. And the secondary effects, ozone destruction, atmospheric chemistry changes, disruption of the food chain, would be devastating on a global scale. Fortunately, No known magnetar is anywhere near this close to Earth. The nearest known magnetar is thousands of light years away, but the Milky Way contains perhaps 1,000 or more magnetars, many of which have not yet been detected because they're in quiet phases. We cannot be entirely certain that no magnetar exists within a dangerous distance. Most magnetars are difficult to detect when they're not actively flaring. A quiet magnetar, one that hasn't produced a burst in decades or centuries, could potentially exist within a few hundred light years of Earth, without our current instruments being able to find it. It's also worth noting that magnetars are not the only objects that produce giant flares. Some astronomers have proposed that certain short gamma-ray bursts, brief flashes of gamma rays detected from other galaxies, might actually be giant magnetar flares rather than the merging neutron stars that are the more commonly accepted explanation. If this is true, it means magnetar flares can be so powerful that they're detectable not just across our galaxy, but across intergalactic distances. A single event on a 12-mile wide star, visible from millions of light years away. That's an almost absurd amount of energy concentrated into an almost absurd amount of time from an almost absurdly small source. But giant flares, as dramatic as they are, aren't the only way magnetars affect their surroundings. Even between flares, a magnetar is a persistent source of danger. The surface of a magnetar is incredibly hot, typically around 18 million degrees Fahrenheit, much hotter than the surface of ordinary neutron stars. This extreme heat is maintained partly by the decay of the magnetic field itself. As the field slowly evolves and reconfigures, it deposits energy into the star's crust, keeping the surface hot. The star continuously emits intense X-ray radiation, bathing its immediate surroundings in a constant wash of high-energy photons. Any matter that ventures too close to a magnetar faces destruction long before it reaches the surface. The magnetic field gradient, the rate at which the field strength changes with distance, is what makes the field physically dangerous to extended objects. It's not the field itself that tears things apart, but the difference in field strength between one side of an object and the other. If you were somehow falling toward a magnetar feet first, the magnetic field at your feet would be significantly stronger than the field at your head, because the field strength increases rapidly as you get closer to the star. This difference in force would stretch your body along the field lines and compress it perpendicular to them. At a distance of about 1,000 kilometers from a magnetar, the magnetic field gradient would be strong enough to disrupt the molecular bonds in biological tissue. Your body wouldn't just be killed, it would be physically dismantled at the molecular level. The magnetic force pulling on the electrons in your atoms on the side closer to the star would be measurably different from the force on the side farther away, and that difference would be enough to tear molecules apart. Even at much greater distances, the magnetar's field would be profoundly hostile to technology. At a distance of about half the distance from Earth to the Moon, a magnetar's field would be strong enough to erase every magnetic storage device, every credit card, every hard drive, every magnetic tape within range. At closer distances, the field would induce destructive currents in any conducting material, overloading electrical circuits, melting wires, and destroying any electronic equipment. A spacecraft approaching a magnetar would lose all its electronics long before the crew felt any direct biological effects from the field. The region around a magnetar is, in every meaningful sense, a death zone. Not a death zone defined by a single mechanism, but by multiple overlapping mechanisms, each lethal in its own right. The magnetic field gradient tears apart molecules, The X-ray emission delivers lethal radiation doses. The occasional flares and bursts release catastrophic amounts of energy. The distorted vacuum plays tricks on light and particle physics. And the extreme gravitational field of the underlying neutron star itself, with a surface gravity about 200 billion times stronger than Earth's, would crush any physical structure that tried to land on the surface. A human being standing on the surface of a neutron star would be flattened to a film of atoms less than a millionth of a meter thick by the gravitational force alone, and that's before the magnetic field even gets involved. There is one more aspect of magnetar violence worth discussing. Magnetars don't just produce flares. They also produce what are called quasi-periodic oscillations during and after their giant flares. When the crust of a magnetar fractures during a giant flare, the entire star vibrates. It rings like a bell that's been struck. These vibrations, called seismic oscillations, cause the star's shape to fluctuate slightly. On Earth, seismologists study earthquake waves to understand the interior structure of our planet. On a magnetar, astronomers study the quasi-periodic oscillations in the X-ray emission following a giant flare to understand the interior structure of the neutron star. The oscillation frequencies detected after the December 2004 flare from SGR 1806-20 ranged from about 18 Hz to over 1100 Hz. These frequencies correspond to different modes of vibration of the star, much like the different notes a bell can produce. The lowest frequency modes involve the entire star vibrating, while the higher frequency modes involve more localized oscillations of the crust. By analyzing these frequencies, astronomers can constrain the properties of neutron star matter, the equation of state that describes how matter behaves at nuclear densities. This is physics that cannot be studied in any laboratory on Earth, because no laboratory can create the densities and pressures that exist inside a neutron star. The quasi-periodic oscillations also confirm that the giant flare was indeed caused by a fracture of the star's crust. The vibration patterns are consistent with what you'd expect from a rigid crust that has suddenly cracked and is ringing with the energy of the fracture. It's seismology on a cosmic scale. Studying starquakes on objects thousands of light years away by analyzing the patterns in their X-ray emission. So let's take stock of what we've learned about magnetar violence. The magnetic field of a magnetar stores enormous amounts of energy in the star's crust. This energy builds up over time as the field evolves and stresses the crustal material. When the stress exceeds the breaking point of the crust, which is the strongest solid material in the universe, the crust fractures in a starquake. The sudden release of magnetic energy creates fireballs of superheated plasma, electrons, positrons, and intense radiation. Small fractures produce small bursts. Larger fractures produce intermediate flares, and the largest fractures, involving catastrophic rearrangements of the magnetic field, produce giant flares that can release more energy in a fraction of a second than the sun produces in hundreds of thousands of years. These giant flares are so powerful that they can be detected across the entire galaxy. The December 2004 event from SGR 1806-20 briefly ionized Earth's upper atmosphere from a distance of 50,000 light years. If a similar event occurred from a magnetar within 10 light years, it could trigger a mass extinction on Earth by destroying the ozone layer. Even between flares, a magnetar's surface emits intense X-ray radiation, and its magnetic field creates a zone of destruction extending thousands of kilometers from the star, where molecules are torn apart by magnetic field gradients. Magnetars are not dangerous in some vague, abstract, theoretical sense. They are dangerous in a specific, physical, measurable sense. They produce real effects on real matter across real distances. They have already affected Earth's atmosphere from the other side of the galaxy. And if one were close enough, the consequences would be existential. No shield, no bunker, no planetary defense could protect against a magnetar giant flare at close range. The radiation moves at the speed of light. By the time you see it, it's already hit you. There is no warning. There is no defense. There is only distance. And the distances of space, vast as they are the only thing that protects us from the most dangerous stars in the universe. The question that remains is how we found these objects in the first place, how many of them are out there, and what their existence tells us about the universe we live in. Because magnetars aren't just cosmic threats, they're also cosmic laboratories, places where the most extreme physics in the universe plays out in ways we can observe and measure and learn from. And the story of their discovery, of how we went from complete ignorance about these objects to understanding them as the most magnetically extreme objects in existence, is a story about human ingenuity in the face of the universe's most baffling mysteries. The story of how we discovered magnetars is itself a remarkable journey through decades of confusion, failed explanations, and ultimately one of the most elegant theoretical predictions in modern astrophysics. Because magnetars weren't found by someone pointing a telescope at the sky and spotting something new. They were found by instruments detecting bursts of energy so strange, so unexpected, that for years nobody could explain what was producing them. The story begins on March 5th, 1979. On that date, a burst of gamma rays swept through the inner solar system. It was detected by multiple spacecraft, including the Venera 11 and Venera 12 probes, which were Soviet missions then drifting in heliocentric orbit, and several American military satellites that were secretly monitoring Earth's atmosphere for nuclear weapon tests. These military satellites, part of a program called Vela, had been designed to detect the gamma ray signature of nuclear explosions in Earth's atmosphere or in space. They were watching for violations of the Nuclear Test Ban Treaty, but on that March day, they detected something that wasn't a nuclear weapon. It was something far more powerful, and it came from deep space. The burst was extraordinarily intense. It arrived from the direction of a supernova remnant in the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way about 160,000 light-years from Earth. The burst lasted less than a second, but its peak intensity was enormous. It was over 100 times more intense than any previously recorded extrasolar gamma ray burst, instantly becoming the brightest such event ever detected. This event, which came to be known simply as the March 5th event, was baffling. It began with an incredibly sharp initial spike lasting less than a quarter of a second, followed by a pulsating tail that lasted about 3 minutes. The pulsations had a period of about 8 seconds, meaning the source was rotating once every 8 seconds. This periodicity was crucial. It told astronomers that the source was a compact object, something small enough to rotate that quickly, almost certainly a neutron star. But there was a problem. The energy released in these bursts was far greater than anything known neutron stars could produce through their normal mechanisms. Ordinary pulsars emit radio waves and some X-rays, but they don't produce sudden, enormous bursts of gamma rays like this. Something else was going on. something more extreme than a regular neutron star. Over the following years, more bursts were detected from this source and from a handful of others scattered across the sky. Astronomers classified these objects as soft gamma repeaters, or SGRs, because they produced repeated bursts of gamma rays at energies somewhat lower than the hardest gamma ray bursts coming from distant galaxies. 3 soft gamma repeaters were identified during the 1980s, each one associated with a supernova remnant, which confirmed that the sources were indeed neutron stars formed in supernova explosions. But the mechanism behind their bursts remained a mystery. Meanwhile, a separate class of mysterious objects was being discovered by X-ray telescopes. These were neutron stars that emitted unusually strong and steady X-ray radiation, much brighter in X-rays than their slow rotation rates should allow. Ordinary pulsars derive their energy from their rotation. As a pulsar spins, its magnetic field sweeps through space like a lighthouse beam, converting rotational energy into electromagnetic radiation. The pulsar gradually slows down as it radiates energy away. But these anomalous X-ray sources were spinning relatively slowly, completing one rotation every 5 to 12 seconds. At these slow rotation rates, a normal pulsar shouldn't be producing much X-ray emission at all. And yet these objects were shining brightly in X-rays, pouring out far more energy than their rotation could account for. Astronomers called them anomalous X-ray pulsars, or AXPs, because their behavior didn't fit any existing model. For years, SGRs and AXPs were studied as separate phenomena. They seemed like different types of objects with different properties. SGRs produce dramatic gamma ray bursts. AXPs produce steady, anomalously bright X-ray emission. But gradually astronomers began to notice similarities. Both types of objects were neutron stars. Both had similar rotation periods in the range of about 5 to 12 seconds. Both were spinning down, losing rotational energy at rates that implied very strong magnetic fields. And both were associated with young supernova remnants, suggesting they were relatively young neutron stars. This is where Robert Duncan and Christopher Thompson entered the picture. In a series of papers published in the early 1990s, beginning in 1992, they proposed a unifying explanation for both SGRs and AXPs. Their idea was elegant and bold. They proposed that both types of objects were neutron stars with ultra-strong magnetic fields, far stronger than those of ordinary pulsars. Fields strong enough that the decay of the magnetic field itself could power the observed X-ray emission, and fields strong enough that sudden rearrangements of the field could explain the violent gamma ray bursts. Duncan and Thompson called these objects Magnetars. They argued that the anomalous X-ray emission of AXPs was powered not by the star's rotation, as in ordinary pulsars, but by the slow decay of the magnetic field. As the ultra-strong field gradually decays over thousands of years, it deposits energy into the star's crust, heating the surface and producing steady X-ray emission. This explained why AXPs were so bright in X-rays, despite spinning relatively slowly. They weren't powered by rotation. They were powered by magnetism. For the SGRs, Duncan and Thompson proposed that the violent gamma ray bursts were caused by starquakes, sudden fractures of the neutron star's crust triggered by stresses from the evolving magnetic field. The energy released in these fractures would explain the enormous gamma ray bursts. And the gradual buildup and sudden release of magnetic stress would explain why the bursts were intermittent, occurring irregularly with long, quiet periods between active phases. The Magnetar model made several specific predictions that could be tested against observations. First, it predicted that the magnetic fields of SGRs and AXPs should be extraordinarily strong in the range of 10 to the 14 to 10 to the 15 gauss. This field strength could be estimated from the rate at which the stars were spinning down. A stronger magnetic field causes a neutron star to lose rotational energy faster. So by measuring how quickly the star's rotation period was increasing, astronomers could estimate the field strength. When they did this calculation for SGRs and AXPs, the results were consistent with the Magnetar prediction. The implied field strengths were indeed in the range of hundreds of trillions of gauss, far stronger than ordinary pulsars and exactly in the range that Duncan and Thomson had predicted. Second, the model predicted specific patterns in the timing and energy of bursts. Small bursts should be common, large bursts should be rare, and the energy release should correlate with the magnitude of the crustal fracture. This was consistent with the observed behavior of SGRs, which produced many small bursts, punctuated by occasional much larger flares. Third, the model predicted that SGRs and AXPs should sometimes be interchangeable. An SGR might show AXP-like behavior between bursts, and an AXP might occasionally produce SGR-like bursts. This prediction was dramatically confirmed when several AXPs were observed to produce bursts of gamma rays, and several SGRs were observed to show steady, anomalous X-ray emission between their burst episodes. The two classes of objects were not separate phenomena. They were the same thing seen in different states of activity. They were all magnetars. The December 2004 giant flare from SGR 1008 106-20 was perhaps the most spectacular confirmation of the Magnetar model. The energy of the flare, the pulsating tail, the quasi-periodic oscillations in the X-ray emission following the flare, all of these matched the predictions of the Duncan and Thomson model with remarkable precision. The oscillation frequencies observed in the tail of the flare were consistent with the star's crust vibrating after a massive fracture, exactly as the starquake model predicted. The event was a triumph for the Magnetar theory, and removed virtually all remaining doubt that these objects were real. Today, the Magnetar model is firmly established. About 30 magnetars have been confirmed in the Milky Way through a combination of X-ray and gamma-ray observations. They include both objects originally classified as soft gamma repeaters and those originally classified as anomalous X-ray pulsars. The distinction between these two categories has largely been abandoned, as astronomers now recognize them as the same type of object observed under different conditions. But 30 confirmed magnetars out of a galaxy containing hundreds of billions of stars raises an obvious question. Are there really only 30? The answer is almost certainly no. 30 is the number we've detected, not the number that exists. Magnetars are difficult to detect for several reasons. First, their active lifetimes are relatively short by astronomical standards. The ultra-strong magnetic field of a magnetar decays over time. As the field weakens, the star produces less X-ray emission and fewer bursts. After roughly 10,000 years, the field has decayed enough that the magnetar becomes much quieter, harder to distinguish from an ordinary neutron star. It effectively retires, fading from view as its defining characteristic, its extreme magnetic field, dissipates. This means that the magnetars we can detect are all young, recently born from supernovae within the last 10,000 years or so. Older magnetars whose fields have decayed below the threshold for producing detectable emission would blend into the background population of ordinary neutron stars. They'd still be out there, spinning slowly through space, but we wouldn't recognize them as former magnetars. Given the rate of supernovae in our galaxy, roughly 2 per century, and assuming about 10% of neutron stars are born as magnetars, the Milky Way should have produced millions of magnetars over its history, but only the youngest, most active ones are visible to our current instruments. Second, many magnetars might be in quiet phases between periods of activity. A magnetar can go years or even decades between burst episodes. During these quiet periods, it emits steady X-ray radiation, but at levels that might be too faint to detect from across the galaxy. A magnetar on the far side of the Milky Way, obscured by gas and dust, emitting only low-level X-rays and not currently producing bursts, would be extremely difficult to find with current technology. Astronomers estimate that the total population of active magnetars in the Milky Way at any given time might be a few hundred to a few thousand. Most are simply too faint, too distant, or too quiet to detect. As our X-ray telescopes improve, as we build more sensitive instruments and launch them into space, we'll likely discover many more. Each new detection adds to our understanding of how common these objects are and how they're distributed throughout the galaxy. The short, active lifetime of magnetars also tells us something important about their nature. A magnetar's magnetic field, as powerful as it is not permanent. It decays. The field loses energy over time, gradually weakening as the energy is converted into heat in the star's crust and radiated away as X-rays. This decay is what powers the steady X-ray emission that makes magnetars detectable in the first place. The magnetic field is essentially burning itself as fuel, consuming its own energy to heat the star. After about 10,000 years, the field is weakened enough that the magnetar transitions into something more like an ordinary neutron star. It still has a magnetic field, still stronger than most pulsars, but no longer in the extreme magnetar range. The bursts stop. The anomalous X-ray emission fades. The star continues to cool and spin down, eventually becoming a cold, dark, slowly rotating neutron star drifting through the galaxy, indistinguishable from the billions of other dead stellar remnants scattered throughout the Milky Way. This means that the magnetars we observe today are all young. They were born in supernovae within the last few thousand years. The December 2004 flare came from a magnetar estimated to be only a few thousand years old. The star was born in a supernova explosion that would have been visible from Earth thousands of years ago, though no historical record of it has been definitively identified. It's possible that some of the guest stars recorded by ancient Chinese astronomers, sudden new stars that appeared in the sky and then faded over weeks or months, were the supernovae that produced magnetars we observe today. Now, let's address the question that might be the most pressing one in your mind. Could a magnetar ever actually threaten Earth? We've talked about what would happen if a magnetar were close enough, how its flares could strip away the ozone layer, how its radiation could trigger mass extinctions. But how realistic is this threat? Should we actually be worried? The honest answer is that the threat is real, but extremely small. No known magnetar is anywhere near close enough to pose a danger to Earth. The nearest known magnetar is several thousand light years away. At that distance, even a giant flare like the 2004 event produces no lasting effects on Earth beyond briefly measurable, ionospheric disturbances. We are protected by distance, and distance is the only protection that matters against a magnetar. But could there be an undiscovered magnetar closer to Earth? It's possible, but unlikely. Magnetars are born in supernovae, and supernovae are conspicuous events. A supernova within a few hundred light years of Earth would be an extraordinarily bright event in the night sky, visible even during daylight, and it would leave behind a visible supernova remnant, an expanding shell of hot gas that glows in radio waves and X-rays for thousands of years. We've mapped the supernova remnants in our galactic neighborhood fairly well. None of the known nearby remnants appear to contain magnetars. However, there's a subtle caveat. Magnetars can receive a kick during their birth supernova. The explosion is often asymmetric, and the resulting neutron star can be launched at speeds of hundreds of kilometers per second. Over thousands of years, a fast-moving magnetar could travel tens of light years from its birth site, making it harder to associate with its remnant. And if it's currently in a quiet phase, it could potentially go unnoticed. Still, the probability is very low. The combination of factors required: a supernova close to Earth, producing a magnetar, that magnetar happening to be in an active phase and producing a giant flare directed toward our planet, makes the overall probability of such an event vanishingly small during any human lifetime. The danger exists in principle, but it's not something that keeps astronomers awake at night. What does keep astronomers fascinated is the scientific value of magnetars. Because beyond their capacity for violence, magnetars are amongst the most valuable natural laboratories in the universe. They allow us to study physics under conditions that are impossible to recreate on Earth and may never be recreatable by any civilization, regardless of its technological sophistication. Magnetars test our understanding of quantum electrodynamics, or QED, the theory that describes how light and matter interact. QED is one of the most successful and precisely tested theories in all of physics. Its predictions have been confirmed to extraordinary accuracy in laboratory experiments. But those laboratory tests involve relatively weak electromagnetic fields. The predictions of QED in ultra-strong fields, the regime where vacuum birefringence and photon splitting and magnetic pair production become important, have been much harder to test. Magnetars provide the only natural environment where these extreme QED effects are significant. By observing magnetar emission and comparing it to theoretical predictions, astronomers can test QED in a regime that no earthly experiment can access. Magnetars also test our understanding of nuclear physics at extreme densities. The interior of a neutron star is one of the densest environments in the universe, second only to the interior of a black hole, which we can't observe at all because nothing escapes from beyond the event horizon. The matter inside a neutron star is compressed to nuclear density, meaning the neutrons are packed as tightly as the protons and neutrons inside an atomic nucleus. But unlike an atomic nucleus, which contains at most a few hundred particles, a neutron star contains roughly 10 to the 57th neutrons, all packed together. Understanding how matter behaves under these conditions is one of the great challenges of nuclear physics. The quasi-periodic oscillations observed after magnetar giant flares provide a direct window into this extreme physics. The frequencies at which a magnetar vibrates after a starquake depend on the properties of the matter inside it. Different theoretical models of ultra-dense matter predict different oscillation frequencies. By measuring the actual frequencies and comparing them to predictions, astronomers can constrain which models are correct and which are wrong. This is nuclear physics conducted on a cosmic scale, using a 12-mile wide laboratory located thousands of light years away. Magnetars also contribute to our understanding of general relativity, Einstein's theory of gravity. The gravitational field at the surface of a neutron star is about 200 billion times stronger than Earth's surface gravity. Light emitted from the surface is significantly redshifted as it climbs out of this deep gravitational well. The space-time around a neutron star is measurably curved, and this curvature affects the paths of photons, the timing of pulsars, and the apparent size and shape of the star as seen by distant observers. Observations of magnetar emission can be used to test general relativistic predictions in the strong field regime, complementing tests conducted using other systems like binary pulsars and black hole mergers. There's also a connection between magnetars and some of the most mysterious phenomena in modern astronomy. Fast radio bursts, or FRBs, are brief, intense pulses of radio waves that were first detected in 2007. They last only milliseconds but release enormous amounts of energy. Most FRBs come from distant galaxies, millions or billions of light years away. For years, their origin was completely unknown. Dozens of theories were proposed, ranging from colliding neutron stars to alien civilizations. In 2020, a breakthrough occurred. A fast radio burst was detected from within our own galaxy, from the direction of a known magnetar called SGR 1935 plus 2154. This was the first time an FRB had been definitively associated with a known source. The detection strongly suggested that at least some fast radio bursts are produced by magnetars, though the exact mechanism is still being debated. If magnetars are responsible for FRBs, it means these tiny, violent, 12-mile wide stars are producing signals detectable across billions of light years of space. That's an almost incomprehensible reach for such a small object. As we look back over everything we've explored tonight, a picture emerges of an object that exists at the absolute extremes of what the universe is capable of producing. A magnetar begins as a massive star, tens of times heavier than our sun, burning through its nuclear fuel in a cosmic heartbeat. It dies in a supernova, one of the most powerful explosions in nature. Its core collapses into a neutron star, an object so dense that a teaspoon of its material outweighs mountains. And in the first seconds of that neutron star's existence, a furious dynamo amplifies its magnetic field to strengths that dwarf anything else in the known universe. That magnetic field changes everything around it. It distorts atoms into shapes that shouldn't exist. It bends and splits light. It gives empty space optical properties. It stores enormous energy in the star's crust and releases that energy in catastrophic flares that can be detected across the galaxy. It makes the magnetar a persistent source of intense X-ray radiation and an intermittent source of the most violent outbursts observed anywhere in the cosmos. A magnetar is dangerous not in some vague or metaphorical sense. It is dangerous in a precise, physical, measurable way. Its flares have already affected Earth's atmosphere from 50,000 light years away. A closer event could strip our ozone layer and trigger a mass extinction. Its magnetic field can dismember molecules at distances of hundreds of kilometers and erase electronics at much greater distances. Its surface gravity would flatten any physical structure into a film of atoms. Every mechanism of destruction you can imagine, radiation, magnetic force, gravitational crushing, molecular disruption, a magnetar possesses them all, amplified to degrees that make every other natural hazard seem gentle by comparison. And yet, magnetars are also beautiful in their extremity. They are natural laboratories where the most exotic physics in the universe plays out in real time. They test our theories of quantum electrodynamics, nuclear physics, and general relativity under conditions we can never recreate. They may be the engines behind fast radio bursts, linking 12-mile-wide objects to signals detectable across the observable universe. They are seismological instruments, their starquake vibrations telling us about the properties of matter at densities we can barely calculate. They are clocks, their spin rates encoding information about the forces that shape them. They are, in every sense, objects at the frontier of human knowledge. The universe contains many dangerous things. Black holes that swallow everything that crosses their event horizon. Supernova explosions that outshine entire galaxies. Gamma-ray bursts that sterilize corridors of spacelight years long. But magnetars occupy a unique position among these cosmic hazards. They are small, just 12 miles across, yet their influence extends across light years. They are temporary. Their extreme fields lasting only thousands of years, yet their effects can shape the fate of biospheres across an entire galaxy. They are rare, perhaps only a few hundred active at any time in the Milky Way, yet they produce some of the most energetic events ever observed. There is something almost paradoxical about a magnetar. It is the corpse of a giant star, the dead remnant left behind after a catastrophic explosion, and yet it is one of the most active, energetic, and violent objects in the cosmos. Death produced it, but it is far from inert. It crackles with energy. It shakes with starquakes. It erupts with flares that outshine stars billions of times more massive. It is a dead star that is more dangerous than most living ones. And all of this, every bit of the destruction a magnetar is capable of, traces back to one thing: the magnetic field. Take away the field, and a magnetar is just an ordinary neutron star. Dense, yes. Hot, yes. Spinning, fast, yes. But manageable, predictable, quiet. It's the magnetic field that transforms a neutron star from an exotic curiosity into the most dangerous star in the universe. The field is the weapon. The field is the engine of destruction. The field is what makes a magnetar. So the next time you hold a refrigerator magnet and feel it tug gently at a paperclip, remember that the same fundamental force, electromagnetism, the same basic phenomenon that lets a small magnet hold a grocery list to your fridge, is the force that powers the most violent objects in the cosmos. The difference is only one of degree, but that difference in degree spans 15 orders of magnitude, from the 50 gauss of a refrigerator magnet to the 1 quadrillion gauss of a magnetar. And across that unimaginable gulf of intensity, the character of the force transforms completely. What starts as a gentle, useful, everyday phenomenon becomes something that can reshape atoms, fracture the strongest material in the universe, and unleash explosions visible across an entire galaxy. We are safe from magnetars tonight. The nearest one is thousands of light years away. The distances of space, those vast empty gulfs between the stars, protect us more thoroughly than any shield or technology ever could. But they're out there. Right now, as you listen to these words, there are magnetars in our galaxy whose crusts are slowly building up stress, whose magnetic fields are quietly evolving, whose surfaces are radiating X-rays into the void. And at some unpredictable moment, one of those crusts will crack. One of those fields will snap into a new configuration. And a burst of energy beyond human comprehension will erupt from a dead star 12 miles across and race outward at the speed of light, crossing the galaxy in 100,000 years, arriving at distant worlds without warning and without mercy. The universe built these objects from the same physics that built everything else. The same gravity, the same nuclear forces, the same electromagnetism, the same laws of nature that allow flowers to grow and human hearts to beat also allow magnetars to exist. There is no separate set of rules for the violent and the gentle. It is all one universe, operating under one set of laws. And those laws permit extremes that are difficult to accept. The most dangerous star in the universe is out there. It is small and dense and unimaginably powerful. It was forged in fire and death and chaos. It carries within it a magnetic field that rewrites the rules of matter and energy. And it will, at some unknowable moment, unleash its fury across the stars. We are lucky to be far away. We are lucky that the distances of space are as vast as they are. And we are lucky to be the kind of beings who can understand these things, who can look across thousands of light years and comprehend what's happening on the surface of a dead star smaller than a city. That understanding, that ability to grasp the danger and the beauty simultaneously, is itself a remarkable thing. It is a product of the same universe that produces magnetars, the same atoms, the same forces, the same physics. We are the universe understanding its own most dangerous creations. And that is perhaps the most extraordinary thing of all. Thank you for joining me on this journey into some of the most extreme physics the universe has to offer. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the cosmos. And the next time you look up at the night sky, remember that scattered among those quiet points of light are objects of almost incomprehensible violence. Dead stars with magnetic fields strong enough to reshape the fabric of reality itself. They are far away. They're silent from this distance, but they are there. And they are the most dangerous stars in the universe. Good night, and sleep well under the stars.